to welcome to the stage legendary Luca.
Thank you. Thank you for the intro. I really appreciate that. You're very kind, too kind in my opinion, but I didn't do much apart from pushing to the right direction. With that said, welcome. So today, I was here last year. I don't know how many of you that were last year at my talk. Okay, a few of you. So last year I was talking about Lambda under the hood, and I thought it was like quite cool. You know, we don't always share what is happening behind the scene in AWS services, but in that case, yeah, we did. And today I thought, okay, so what's a good segue from there? We could talk about some best practices to implement, let's say, great performances in Lambda functions. But obviously, you know, the thing that I don't like much is, oh yeah, we have this slide that tells you that, this slide tells you that, and no one is trying. So I built something, why not? And today, basically, I walk you through my reasoning, so just to help you to apply exactly the same reasoning on your next serverless workload. That I think is always great to say, understand. I think it's very difficult to understand what's going on when a developer is trying to apply something, unless you speak with a developer. And therefore, the agenda for today is this one. So we're going to talk about, first, a bit of a recap, what's happening underneath the Lambda service. And then we're going to talk about a solution that I'm not great with names, an optimized solution. And then we move into the design and improvement approach, so my train of thoughts or stream of consciousness, depends how you want to call it. And we look into the optimized solution, and then if you have any question, happy to answer. Let's start with that, like a couple of slides, just to understand and frame where you can operate to make your Lambda function better. So this is basically the architecture of a Lambda service, high level, obviously. So you can have multiple sources on the far left of this slide that could invoke a Lambda. It could be synchronous, it could be asynchronous, and depends from the type of integration. We have different ways that are going to call the front-end service. That is the one responsible for, let's say, assigning to a worker manager the request that something has to happen. And then at some point, what we do is we assign to a specific worker basically the invocation, and we spin up a micro VM. And in all of that, the only thing that you take care of is the worker, or better, sorry, the micro VM part, or what is inside the sandbox, because we do all the rest for you. And that's, in my opinion, the beauty of this solution. The other cool thing is that obviously we have availability in mind, and therefore we try to provide you with the scalability and availability that is needed in order to make resilient your APIs, website, whatever you are running inside Lambda function. And I think it's something that you don't have to underestimate, because it's not as easy as you might think. If you had dealt for a while with VMs and containers, stuff like that, you know better than me that you need to configure quite a lot of stuff behind the scene, making sure to scale a certain piece. And just to give you an idea of what kind of volume we are talking here, Lambda service is dealing with over 10 trillion of requests per month. That is a data point from last year. So just to give you the idea of the scale of the operation. The thing is all great, and I think it's amazing understanding how Lambda is working under the hood, because it gives you also more context on how to build things. But more importantly, we need to understand where we can impact the design of our Lambda functions. And it's usually understanding this. This one is by far my favorite diagram that you can find in the AWS documentation, that is under the extensions side, and basically shows that we have three phases. As you can see here, we have the initialization phase, the invocation phase, and the shutdown phase. Those three phases are how your sandbox will work, where your code is running, right? The two parts that you really care about are, first of all, this part, the function initialization, that is, let's say, when you really initialize your code. So everything that basically is outside the function handler. And you care about also the invocation part, right? So the two yellow, let's say, rectangles are the ones where we can have an impact. So initialization is happening only when we spin up a new micro VM. So there is a request. Let's assume that is the first time that someone called that API. And then at that stage, we spin up a micro VM, we grab your code, we have a runtime that is cached inside the worker, and we just, let's say, initialize the function, and then we execute the function. From that point on, because that micro VM is already there, you will start to have just the invocation phase. So the initialization phase won't be triggered anymore till a new micro VM is spinned up. Okay, now that we have the basics, let's start with what I call an unoptimized solution. Let's say when I was working on this, I thought, okay, what can we do for creating something that is, let's say, similar to what other people would build? This is a classic CRUD API. Where you have like an API gateway is exposing a Lambda function. We are working inside a VPC here, so therefore we have a Lambda that is VPC attached to my specific private network that I created. I'm using RDS proxy and Amazon Aurora for storing my Postgres database and all the data related to NFL stadiums. And then I have a bunch of other stuff that I rely on, so a bit of observability. I have X-ray for distributed tracing. I have CloudWatch for logs and metrics, obviously IAM. And then I also, obviously, I want to store some information in parameter store because I want to tweak, let's say, my behaviors of Lambda on the fly. On all of this, usually, if I think how I've seen customers dealing with these kind of workloads, they just pick, let's say, one of the architecture. We have two architecture available. Very often, I've seen x86 as a first choice. That's basically what I build. It's like something that maybe you have built yourself for few applications. Okay, so first and foremost, when let's say, usually what we recommend is that when you build your application and you create, in this case, an API, you have outside the handler a couple of optimizations. Like, for instance, if you want to fetch the parameters from parameter store, you don't have to do in every single execution, because otherwise it means that you need to create a connection with parameter store, you need to make a request, retrieve the information, and then apply that inside your logic. That add latency to your response time. That is not great for the users. And therefore, what we recommend is, if you consider the ephemeral nature of a Lambda function, to, let's say, have this kind of requests that are happening outside the handler. So you just do an initialization phase, and then when you have the execution phase, so when basically the Lambda is triggered over and over again in the same micro VM, you already have the data there. Are in memory, are stored for the entire life cycle of that specific micro VM, and you're good to go. So usually this is a best practice that we recommend. Now, you have seen before that I was talking about RDS proxy, that if you're using RDS, it's a really great service for a couple of reasons. Because, first of all, one of the challenges you have with Lambda, especially because you cannot control the scale, so if you have like 1 million requests in a minute, then you are going to have multiple micro VM that are hitting your database. But you need to deal with connection pool. That is one of the key things. And RDS proxy takes care of that for you. The other thing that takes care of is secrets and certificates management. So if you want to deal with the secrets, you don't have to retrieve that in your Lambda function. You just ask to RDS proxy to handle that. That is very convenient, I would say, because it's not that it's complicated to build, but still you need to maintain that code. So if you don't have to, why not? So RDS proxy was a good solution for this example, so we went with that one. Remember, another thing that when I was building this, I think was important to highlight very often is, let's say, not highlighted it too often, but all the libraries for, let's say, Node.js in this case, because I'm a JavaScript developer, you find online will enables you to set up, let's say, a pool of max min connection. There are usually some, let's say, good documentation in every single library that I found. In this case, it's SQLize for handling let's say, the configuration of a pool inside a Lambda function. So check it out, because very often it's not, let's say, taken into account. So I highly encourage you for that. Now, there are a few things in Node-land that you need to take care, because vast majority of the time, we need to think about how we can optimize the size of our bundle, as it's called. Why that? Because if you think about that, as I said before, at some point, we spin up a sandbox for you with the runtime, but we need to fetch your code. And the bigger is the package that you're creating, and obviously the longer it will take, because for better or worse, there will be some, let's say, data that are flowing through the network that has to be unpacked, created in memory. The Node.js engine has to put in memory a few things. So it takes time. And the bigger it is, the worse the performance you have. And therefore, minification is something that I didn't see as often as I would like to in Node, TypeScript, and JavaScript. So it's something that you should set up in your configuration. The other thing is this output format. So I'm using ESM for this example, and I will show you later what enables me to do. Usually there is a long discussion in the Node.js community between CommonJS versus ES modules. I know that CommonJS, performance-wise, might be better, but let's say I think we are heading towards an ES module world, ECMAScript module world, and therefore we need to be conscious of the capabilities of this approach. And I really like, to be honest, because later on I will show a couple of experiments that I did leveraging the capabilities of ES modules. The other thing is you have, let's say, a capability with the configuration of a Node.js function that you can decide if you want to bundle certain modules or you want to install and retrieve inside the sandbox. This is basically what you can do with the Node modules. So with this part, you just specifying that these modules will be installed. So for instance, Power Tools, that I talk in a second what it is better to have that installed over minified altogether. And if, considering I have found last year quite a few people in the Node.js community that were struggling to configure CDK with Lambda, I created like this template that basically allows you to download a blueprint, and you have like basically all the configuration and best practices embedded there. So you can use ES modules with Node.js and CDK. Obviously, wherever you see there can be applied then either in AWS SAN. You cannot do in CloudFormation out of the box. You need to split basically the bundling phase from the configuration of your infrastructure, similar to Terraform if you are a Terraform shop. So there you can find very, very quickly what it is. So one thing that we often seen customers struggling with is the observability part. So tracing, logging, metrics, you know better than me. So Power Tools is extremely interesting library. It's a completely open source. There is a team that is dedicated to this library that is available in multiple languages. So if you are a Python developer, you have in Python, you have in Java, you have in .NET, you have in obviously TypeScript and Node. And this is how you initialize the Power Tools inside your Lambda function. So as you can see, you have just activated tracing. I can pass also some configuration of my metrics, logger, and so on. And usually what we recommend is using NIDI, that is a Node.js library that is a middleware. So it's just simplifying the way how you are interacting and integrating your code inside the Lambda function. It was created by an AWS hero, and I believe that is currently quite often used from what I've seen in many examples for Node.js and TypeScript. So Power Tools allows you to do some cool stuff. For instance, when I'm using X-Ray, one thing in performance that matters, and I did like a lot of work in the past as engineer in low latency low latency environments and low-end devices, and also with let's say, embedded devices. So therefore, what we were doing was micro benchmarking. So if you want to understand why in CPU a specific algorithm doesn't work, we were basically setting up a timeout at the beginning, timeout at the end of the algorithm, and start to see where the bottleneck was. And that helped a lot. So I tend to approach everything in the same way. In this case, for me, is I'm using X-ray that allows me to create like subsegments. So I can create a segment and say, okay, this is the segment related to that specific operation. And I tend to have all the information needed every time that I execute the Lambda function. So I can see how the things are performing. So for instance, if I have a library that doesn't perform as expected, I can change the library, and then I know that it's not the code that I've written, but something else that I could handle. And similarly, I can do, thanks to Power Tools, some decoration. So I can create like that at tracer capture method, and I add like a subsegment name, and every time that I invoke that function, I will basically capture that information. And as you can see, it's extremely convenient, because otherwise you need to do that by your own, but with Power Tools, we can do a lot of stuff. Power Tools can be integrated as a library, but also with Lambda layers. You just specify what is your layer and the type of region that you want to have it, and then you just set as external modules inside your Lambda function that stuff, and everything will be done for you. So very easy to integrate. But Power Tools is not only for tracing and observability in general. So you can do more with that. So as you can see, this every single, let's say, library for different languages has different capabilities. But as you can see, this in TypeScript is literally, I just captured that this morning when I woke up. You can see you have some patterns as well, like idempotency is a pattern that you see over and over and over again. So having that out of the box, where you specify basically the DynamoDB table where you want to store your keys, is absolutely great. You have also parameter store integration. You have a parser with the Zod, that is a library for checking the schema of your request and object in general, that is out of the box with Power Tools. And every time, as again, it's open source, so you can see how it's going to evolve. You can even influence the roadmap if you think. Okay, so those are the things that I have implemented in my workload. So let's talk about the testing methodology, because obviously, as I said, I want to, let's say, show you a few things that I've done. So first of all, I use Artillery, again, Node library that enables you to just do load testing. It's like JMeter, if you're familiar with that, but for Nodeland. I tried, let's say, this test from 45 seconds to 2 minutes of sustained loads, and I moved from 20 to 100 virtual users that basically are equivalent to requests per second, okay? Perfect, so let's see how it went. So in the first one, as you can see here, yes, one thing before we start, I want to share also this trick. So if you are looking for cold starts in your Lambda function, in Lambda inside, you can find this information related on how many cold starts you have for a specific function. There is a query, it's very handy, you can find in serverless land. And in the CloudWatch inside, you can find all the information needed for your Lambda. Okay, so with that, we have enough information to say, let's see how it goes. So first test is 10 seconds, ramp up from 0 to 20 requests per second, and then we have a sustain from 20 to 50 requests per second for 50 seconds. Okay, so basically a minute of request. So first thing we notice here is that we had 18 cold starts. So as you can see, the P99 is pretty far away, is over 2 seconds at the moment. And it was, let's say, a gradual and gentle ramp up of my Lambda functions, right? Okay, so the interesting thing is that I started to look into the worst cold start. So the cold start for us is the first time that you're loading a sandbox. So every time you load a micro VM, that is the cold start, because we need to retrieve all the information that I described before. So the worst one they had was 1 second point 43 before executing and return back the response. And then I have the best one was 1.21. Okay. That was basically what I had with TypeScript. It wasn't an hello world. That was just literally querying Postgres, retrieving the information, and sending back to the request that I made. On the other side, we have the warm start. The warm start is basically the micro VM is already there, and they start just to execute things, right? So just skipping the initialization because it's already there, it's just going there. So as you can see in this case, exactly the same query, exactly the same thing, but we started to have like different performance, performance result. So we have 228 milliseconds on one, and the other one, the best one they had was 167. And overall, you know, if you're saying, I have an API, I don't have a specific SLA, it's not too bad overall. Then we look into the second test that instead I'm simulating like a massive spike from 0 to 50 requests per second straight away, like cold start everything. I didn't call for 24 hours that API, just like moving from immediately 50 requests per second. So the results are completely different because obviously, because it takes time for respond for my Lambda function, it means that I need to have more micro VM for supplying the first request because I have like now 50 requests per second, right? So I need to like spin up more micro VM, and then when those have fulfilled that thing, we start to have, let's say, we start to be reclaimed by us, and you will have less based on your volume. So in this case, we have 137 cold starts. Okay, and also the P99 was pretty high, was over 4 seconds because the traffic pattern completely changed. Exactly the same code, right? Perfect. So then I sit down and say, okay, this is quite common. Like I've seen that even before when I was an AWS customer. How can we optimize it? Let's try to play a bit with architecture. So let's start from the architecture part. So on the architecture part, I started to look into, okay, so a few things that I'm seeing in this behavior is that I'm returning a bunch of NFL stadiums. How often the NFL stadiums are going to change? Not that much. I could cache in memory of my Lambda function, but that means every time that a Lambda function is spin up, because are, let's say, independent, I cannot share what is in memory. So I need to do that operation every time. Or I can share the cache. And therefore, I started to add Elastic Cache in the mix. And Elastic Cache, what it does is literally it's just Redis that I implemented a cache side pattern that is very easy to implement. And therefore, I said, okay, that's not a bad idea at all. The other thing I thought is, okay, but you know, ARM is another type of architecture you can have with Lambda. You can reach up to 20% better performance with ARM, but we need to have a more deterministic way to understand where we are going. Because before, I was just guesstimating how much memory I need, right, on my Lambda function. And also I have to guesstimate a bunch of other things on my configuration. So this is basically how the logic works. First thing is I receive a request, I check if there is something in the cache. If there is, I return the data in the cache, otherwise I go to Postgres and so on. But that means I can create, let's say, a cache that has a specific eviction time, and therefore I don't hit Postgres that often, and everything became extremely fast. The other thing is, as I said, work on embedded system. Therefore, one thing that you do in embedded system is always checking the library size and code size. So the one that we're using SQLized, when I was bundling my output, it turns out that it was 1.6 megabytes of Lambda function. I know that the number seems small, and absolutely, but just to show you the power of doing a bit of analysis. So when I started to analyze, I said, okay, I'm not doing any magic there. And yes, SQLize is helping, and it's the most used, if you do a research, it's the most used Postgres data library that you can find there. However, you can find something that is different. So Postgres, so the problem with SQLize is that it's not tree shakeable. What it means is that we cannot remove the unnecessary methods inside my my code, and therefore it means that I'm bundling the entire library every single time. So I was looking for something that was tree shakeable, like Postgres.js. Postgres.js is a library that was created with the ES6 in mind, ES modules in mind, and as you can see, just changing the library, the underneath library for doing exactly the same query, moved the needle quite a lot. Now, this number is not true. In reality, it was 42 kilobytes, the result that I had just like for like removing the library. Why that is 200? Because I started to add also the Redis library and a few other things. So that is the final bundle that I have. But as you can see, massive win. Think about in scale, if you have like a 10 meg bundle or whatever, you can save quite a lot of stuff. So we said we have minification, but the other thing that we need is tree shaking. Tree shaking, let's say, is a very important capability when you're using Node.js, because not all the libraries are designed for that, but if you can, it means that you are going to bundle inside your code just the code that you're using and not the code that you are not. And that is extremely helpful. The other thing that I did is I said I'm tired to guesstimate my, let's say, memory size for my Lambda function. There is a solution, completely open source, was created by an Amazonian, that is called power tuning. So power tuning enables you to run a step function inside your AWS account and test with different memory size your Lambda function. Therefore, the code is exactly what you have written. The environment is the same, so you can start to look into that. So in this case, for instance, that was the unoptimized version. You can see that I was selecting, that I've seen very often, the lowest memory that you can have in Lambda function, 128 megabytes. And as you can see, so the red one is the invocation time, and the blue one is the invocation cost. So the cost was okay, but the invocation time was very high. If I just move the needle to my memory size to 200, sorry, it was 256 in this case. So I moved to 512 megabyte of memory. The cost was the same, but the response time was way faster. And with this tool, I can start to, let's say, stop guesstimate how would be the behavior of my Lambda function, and make multiple tests just to understand when I do massive changes where I'm landing to. And then I can also decide if I want to optimize for cost, for performance. The other thing is, when you look into the optimized solution, the one that I showed you before, here is the sweet spot for cost and performance. So when I'm around 512 megabytes or 1 gig, I can have similar cost, but performance pretty good. So that was another indication that I really like that. Then I thought, okay, but that's not enough. I want to do more. So what if I take out the parameter store from the initialization phase, and I use an extension for loading the information parameter store. There is an extension that enables you to fetch data from parameter store and secrets manager, and that enables you to basically have also the cache out of the box. So you don't have to think about, oh, I need to cache or whatever. You can configure this information directly when you are setting the environment variable. So you can set, okay, I want a TTL of my cache of 100 milliseconds and so on. So as you can see, you have a bit of flexibility. There are a bunch of things and configuration that you can have, and you can find more inside the documentation here. And the interesting part is the implementation. It was trivial. So I just, let's say, have an HTTP request, because what the extension does is spinning up a web server inside your sub-process. And then basically you are starting to work into the communication between the two. And basically the extension takes care to call parameter store, cache it, and that is great, because very often if you don't do that and you have a high volume of Lambda functions, you might risk that you find that you hit the quota of parameter store or secrets manager because you call it too often. But instead, if you cache it, then you call once, and for the entire execute, or for the entire time that you set up your TTL, you're not going to evict the cache. You're not going to call parameter store, so you also save some money over there. But moreover, you have better performances. Okay, so remember just one thing that you need to remember in this case, that you need to retrieve also, so if you use this extension, the session token. And the session token is available in the environment variable. It's called AWS_session token, and you pass it as a header. That's the only thing you need to remember. That is out of the box. You don't have to pass this environment variable. We pass that for you, so you just need to use that. Okay, with all of that, let's start to do some tests. So now we move into 9 cold starts. That's not bad, so we add that. So it was 18 before for the gentle ramp up from 0 to 20 and from 50 requests per second to 8. That's great. But the other interesting thing, you see the P99 now? Look at how nice is the P99. It's very close to the 0 run, right? So if you see the worst cold start was under a second. 800 milliseconds, give or take. So also there, we save like half millisecond, 500 milliseconds very easily. The other thing is, the best one was half a second. That was like a good saving over there. Then when we look into the warm start, now we start to have fun. So we have like 73 milliseconds for the worst one. Guess what was the best one? 10. I'm not using Rust, but still, it's pretty good. So 6 milliseconds for the response time. Obviously, you need to add the latency for API gateway and all the other stuff, okay? This is, although, what you can control. The rest you cannot, because you just plug and play stuff, right? Now, the other thing that you need to remember is that you might think, okay, now we have 6 milliseconds, so if I have 100, let's assume that I have 100 milliseconds response time, I have a concurrency limit of 1,000 requests per sandbox. If I have 10 TPS, let's calculate how many I can handle inside the specific sandbox. But the reality is slightly different, because even if we have the response time, it's not that it's equivalent to, okay, I have a sandbox and I can calculate perfectly how many requests per second the sandbox can serve. One thing that you need to remember is that we changed quite a few things last year. And in fact, even in the documentation, we are saying, by the way, don't think about how many response per second a sandbox can handle, but just think holistically on how many requests you have inside your system. What we have changed last year is this. So now you have like a concurrency model that is different. It's a year that is out there. Maybe you didn't even realize if you were using Lambda, but it's pretty cool because now we have like 1,000, a bucket of 1,000 function every time, or better concurrent function every time, or every 10 seconds in this case, and we just grow in this case. So as you can see in this example, I skipped the first few part of the graph, but let's assume when we say like we have 5,500 that are fulfilled, execution environment that are fulfilled, and there is a green box that says 1,000 and 1,000 that is red. So the cap of this account is 7,000 concurrent Lambda functions. We have 5,500 that are already done and spin up and are working perfectly. We add another 1,000 because in 10 seconds we can add 1,000 for that specific function. If there are more, we start to throttle them. A bit because we have half of them that we will be able to fulfill 10 seconds later. But the other thing is because we can afford to spin up like 1,000 more every 10 seconds. And that is another consideration that is important because the traffic pattern of your system is important to understand. Very often when I go to a customer, they tell me, oh, I don't know. But you need to understand that because a traffic pattern helps you to design your serverless architecture properly. So in test 2, when we hammer this API, we start to have like only 9 cold starts. And look how beautiful is the P99. This is like literally from 0 to let's say 50 requests per second. And before was 100 something cold starts. Now we have 9. That's not bad. So just to recap, this is what we have. So we move from worst cold start 1.42 second to 6 milliseconds of optimize and the best warm start. So as you can see, you can do a lot. But I didn't stop there because then I thought, okay, so how much, oh no, this is the duration component, but this one was the interesting one. How much I can squeeze if I don't use the cache? What if I don't use the cache side pattern in the optimized version? So as you can see, there is a significant savings in, let's say, time for the response time when I use the cache and when I don't use the cache. I was just playing with the parameter in my parameter store. So therefore, if we want to recap the performance here, we have done 56 improvement in cold start, but 95 in warm start. Overall, it's not bad at all. But obviously, there is now the mad scientist that hat that I usually have between 9 p.m. onwards. Let's start to think about can we optimize even further. But yes, of course we can. So there is a currently experimental custom runtime called LLRT that is a custom runtime built with Rust and Quick.js. Still, let's say experimental. take with a pinch of salt. What we do is basically a colleague of mine that created that. It offers 10x faster startup and 2x overall lower cost compared to JavaScript, and great, I like that. But bear in mind, there are limitations that you cannot use like full Node. It's just a subset of Node.js, okay? We are trying to improve that, but if you're curious, you can find the information over there. Now, if you look into that README file, you can see a table like that. So as you can see here, you can have like LLRT 128 megabyte with DynamoDB. And if we look into the P99 here, we're talking about in cold start between 83 milliseconds on response time for the Lambda. Instead, with Node 20, same configuration for a put, it was 1.6 seconds, just to give you the bracket of things. So when it came out and it was stable enough for trying out, I tried out. I'm working on one thing, and I'll show you in a second what it is. But first thing, I have API gateway, my Lambda function, VPC attached, and EFS. So I try to do what I was doing inside this example, Node.js 20 with the 512 megabyte, end up to have a response time in cold start of 770 milliseconds. LRT, 160. And I could even reduce the amount of memory of that. That's pretty cool. There are a few customers that currently are using LLRT in production as, let's say, in different workloads, especially for, let's say, maybe non-critical workloads. So it's something that if you don't use, let's say, all the bells and whistles of Node.js, something to think about. Now, the other thing of the example that I was working in that architecture is this one. So, what if? Let's live in the world of what if. In ESM, usually when I have ES modules, I import stuff in this way. So I just like create my Lambda function and import my module and I use it. But what if we start to use an asynchronous import of my modules? And what if I have like what they call a Lambda leaf or a monolithic Lambda that handles all the CRUD logic? And in my handler, I have logic like this, where I have the get, I asynchronously load my module only if and when it's going to be loaded, because let's face it, when you have a CRUD API, vast majority of the time you are having read or having write. And even if you're having writes, it means that you probably do a lot of put or a lot of create, but not much delete. It depends on what is the workload that you are expressing. And if it's in read, maybe you're not going to handle everything on writes. So, in the what if land, I was thinking, what if we take this system where I'm loading this module, and I have Lambda function that is Lambda lead of 2.5 meg, so not big, but just to play with that. And instead of loading the modules from the sandbox, so my sandbox is basically almost empty, therefore a faster cold start. We said how the impact of a large package could have with the cold start. What if I load that from EFS? EFS is a file network system that enables you to share files with all your Lambda functions. It's plugged with the Lambda function, and you can potentially load from there. So the interesting part of this example, that again, I'm still experimenting on this, it's not finalized that, but the thing is, it didn't change much from what I had before, in the architecture that I had before. But what I'm gaining here, think about you have like hundreds of Lambda functions, and you have like a layer that is over there. And then suddenly you decide to change this version of the layer. Now you need to redeploy all the Lambda functions. But what if your library that they are going to share is living on EFS, and you need to update just EFS, and the Lambda automatically have all the modules there? And what if I have a Lambda lead that is fairly complex, and a team with different people are handling, let's say, their code differently? There are a lot of use cases I'm thinking with this solution, but the fact that I can use the ESM for lazy load, basically my module, and load only the code that is needed when it's requested, it opens a lot of interesting thought. Okay, so main takeaways of this call. That's first of all, but choose your libraries wisely. You don't pick like only the latest library or the most used library. Try to understand what is behind that. So use cache where possible. Cache is your friend. You can cache in memory, you can cache on CloudFront, you can cache with Elastic Cache or MemoryDB, whatever. Use it and leverage it for improving your performance. Extension can optimize your workload. You can create even custom extension. For instance, the example before, I was loading ES modules instead of from EFS from an S3 bucket. Create an extension that spin up a nice web server, fetch the stuff from S3, and then enables my Lambda to load the module at runtime. And finally, bundle size models. We saw that. So remember also LLRT, that could be an option to look into. And if you want to drill down into what I discussed during this talk, there is an article I wrote that you can find here. And that's all I got before Mateusz is going to kick me out from this stage. So thank you very much for having me, and I hope that you enjoyed the session.